Welcome to the video on the reverse bias of the PN junction diode. In the previous video, we have discussed about what is meant by a PN junction, how does the diode function when it is forward biased and reverse biased. So here in this video, we will be discussing about what is meant by reverse bias. So when a diode is connected such that the positive terminal of the battery is connected to the P region and the negative terminal of the battery is connected to the N region, the diode is said to be forward biased. So during the forward biased condition, there will be a current flow and the current will be in this direction and the current will be flowing from the P region to the N region. So in the reverse bias condition, so what is meant by reverse bias? So reverse bias is when the P region is connected to the negative terminal of the battery and the N region is connected to the uh, positive terminal of the battery. So here what happens is the diode is reverse biased. So during reverse bias, what happens? So the depletion region increases. So depletion region increases. So the inbuilt electric field increases. So because of that, the electrons and holes will have an opposite force to move further. So there will be no diffusion current. So the only current which comes through during the reverse bias is called as the drift current. So drift current is due to the minority carriers. So here during the drift current process we know that the number of minority carrier is very less and normally the current during the reverse bias will be very small and that current we will be calling it as reverse saturation current. So here we can see that as my reverse voltage is increased from 0, so the voltage is in the negative, so it indicates that there is a reverse voltage is applied. So here the current is very small and the current is represented in terms of microamperes. Now when the input voltage is increased, when it is increased, the current remains constant. So the reverse current is only due to the movement of the charge carriers which are created due to the thermal process. So there is no relation between the applied voltage and the developed current. So the current will be constant throughout the reverse bias region. But when the applied voltage increases such that it crosses a particular voltage, then the breakdown mechanism occurs. So what is what is breakdown? So breakdown is a process in which during the reverse biased condition there is a sudden increase in the current. So here this curve where it bends down is called as the breakdown. So what is meant by breakdown? Breakdown is nothing but we know that the reverse biased condition, the depletion region is developed. Because of that, there will be an opposing force for the charge carriers. It act like an rubber band which will be elongated. The force exerted on the reverse band is elongated, and at one stage, the force breaks down, and that is the junction breakdowns, and suddenly there is a large flow of the current. So the reverse breakdown is mainly depending upon the band gap of the semiconductor as well as the doping of the semiconductor at the junction region or at one side of the region. So for example, N suffix B is the doping of on the lightly doped side of the junction. Then the reverse breakdown voltage VBR is found to be inversely proportional to NB. That is, even though we have two layers or we have two sides across the junction on both the sides of the junction, the lightly doped junction layer of the device will decide the breakdown voltage. So the breakdown voltage is depending upon the lightly doped region.
So it is inversely proportional and it is given as VBR is proportional to 1 by NB to the power 0.75. So here, in this case, we can see in this graph, when we see here, we can see here the doping concentration is given here, whether it is Na or it can be Nd, and also the y-axis is nothing but the breakdown voltage. So here, normally the breakdown voltage will be around 10 volts we will be having. But as we increase the doping, the breakdown voltage also increases. For germanium, we can see that the breakdown voltage is very less is less compared to silicon, and which is very less compared to the gallium arsenide. That is, for a particular doping concentration of 10 power 17, if we can see that the breakdown voltage for germanium is around 7, whereas for silicon it is 12, and for gallium arsenide it is still more. And also we can see that as we increase the doping, as we increase the doping of the semiconductor material, the breakdown voltage decreases even for a small same material. So this breakdown mechanism is of two types. One is called as Zener breakdown and another one is called as avalanche breakdown. So what is meant by Zener breakdown? So during the reverse bias in a very heavily doped diode, the number of the large number of empty conduction band on the N side align with valence band on the P side. If the barrier is small, the electrons from the P side tunnel to the N side. This channeling effect is called as Zener diode. That is, the first condition is the diode should be heavily doped. So when there is heavy doping of it is happening, so we know that our breakdown voltage is inversely proportional to the doping concentration. So the potential barrier, what it is formed, it will be the potential depletion ridge will it will be narrow for a heavily doped region, and hence and also we can say that the electrons which is present will be having enough space to move to the conduction band in case of this Zener breakdown. So in that case, even in the reverse bias, there will be a sudden increase in the current due to the tunneling phenomena. Qualitatively, I can say that this is due to the rupturing of the covalent bond. That is, we know that in a reverse biased condition, in the center, we will be having a depletion region, and depletion region will be consisting of immobile ions and our covalent bond. So when I apply more voltage, the covalent bond will get broken and the free electrons will be coming out from the bond. So that thus resulting in the electrons and the holes. So we can say that Zener breakdown is a mechanism in which there will be a sudden increase in the current during the reverse biased condition. So the VI characteristics is given here, that is during the reverse biased condition at a particular voltage there will be a sudden increase in the current, and that is called as the Zener current. And when I go for the energy diagram, we can see that this is the width of the base region. This is the width of the base region. So normally what happens is a heavily doped junction will be having at equilibrium, it will be like this. So when I reverse bias it, the electrons which is here will be having a space to move to the other space. So there will be an equivalent energy state which the electron can occupy, and due to that there will be a movement of charge carriers, and that is given as and that will result in the current which is called as the Zener current. So this video explains us about what is meant by reversed